Alrighty, in part 2 of chapter 13, we're going to talk about isotopes, okay, and explain what that heavy peak showing up in mass spec was. We will finish mass spec overall. There are a lot of examples from what we're going to cover in this part in your textbook if you want extra practice. Now, if we think about pentane, for example, if we go back and look at that spectrum, right? There was a peak at 72, which we called the molecular ion peak, but then there was also a tiny little peak at 73. So how does that make sense if we thought the molecular ion was the heaviest? Okay. Well, typically in mass spec, we see what's known as this M+1 peak, okay, which is a small peak due to the presence of carbon-13. Okay. 1%, a little over 1% of all carbon is carbon-13, which adds an extra AMU to your atomic mass. Okay. That's typically about 1% of the height of your molecular ion. Okay. So we can see M+1 pretty commonly, and we don't want that to accidentally throw off our calculations. We can even see an M+2 peak, okay, which can give you actually a pretty valuable bit of information we'll talk about in just a second. If you see an M+2, it can be due to a couple of things. Okay? In organic molecules, it can be due to the presence of oxygen-18, which is a minor isotope of oxygen, or it could be a combination of two heavy isotopes that are +1 AMU each. Okay, so a carbon-13 and a deuterium together, right? A plus, so that's M, technically, M+1 + 1 or M+2 overall. Or if you had a large molecule, it's more common to have two carbon-13s. That would give you a M+2, right? But it's 1% of 1% is the probability for you to actually get that. If you see a large M+2 peak, that's a really handy clue in mass spec that you probably have chlorine or bromine in your molecule. Okay? It gives you a larger peak because those are more prevalent natural isotopes. Okay? Thinking about bromine, for example, you've got two isotopes of bromine that are really common. Okay? You've got bromine 78 and bromine 80, both at about 50% apiece. Okay? So if you see your molecular ion and your M+2 at about a 50-50 split, that's a clue for bromine, as we'll see in a second. Okay? Same thing with chlorine. It's about a 1-to-3 ratio of chlorine 37 to chlorine 35. So if you see an M+2 that's about a third of the height of your molecular ion, that's a clue for chlorine. Okay? So we'll see that in a second. Here's a table of natural abundances of isotopes. Anytime you have a heavy isotope, it can give you a heavy peak, just like carbon-13 gives you an M+1. Okay? Sulfur-33 could do the same thing, for example. And you wouldn't see a heavy peak for iodine, for example, because there's no heavy isotope. Okay. And I mentioned this in the first video, right? Mass spec is recording individual molecules, right? Not an average. So when we're calculating an MZ, atomic masses of single isotopes are used. So we use whole numbers, right? If you look at the periodic table for chlorine, for example, it says 35.45, blah, blah, blah. We don't use that in mass spec because no chlorine is 35.45 AMUs. That's the weighted atomic average. Right? We would use 35 if it's chlorine 35, or if it's a heavy isotope, we would use 37. And there are instruments that actually have enough power to determine those individual differences. It's known as high-res mass spec. Okay? Even if something has the same molecular mass, look at all these things down here that weigh 122. High-res mass spec can actually determine those individual differences, those tiny little sig figs. And high-res mass spec will give you the exact molecular mass and give you the formula from that. No rule of 13 or anything to worry about. Okay? Everything we've covered before and everything we will continue to use in this chapter is low-res mass spec because there's a huge price difference, right? But just be aware that high-res does exist. can calculate it to the nearest 10,000th of an AMU so that it gives you the exact formula. No rule of 13 necessary. Okay? That's calculated by using a computer program. About $2-3 million a piece for these high-res instruments. Okay. So as we continue to wrap up in this part, our discussion of mass spec, we need to consider some clues that it can give us about detecting functional groups. Okay. And that comes in fragmentation patterns. We talked about identifying bromine or chlorine, but fragmentation patterns can give you clues about functional groups in mass spec as well. Typically, you're going to get a lot of this information from IR, but you want as many tools in your toolbox as you can get. So if you can recognize the characteristic fragmentation patterns, it can help you confirm the functional groups that are present in these molecules. And we're going to consider a couple of them: alkyl halides, ethers, alcohols, and ketones. Okay. So again, let's look at these alkyl halides, looking at bromine and chlorine. So what are you looking for here? Here's the clue. If you see a molecular ion peak, which on a test would always be labeled for you, okay, I will label the molecular ion peak. So if you see another peak at M+2 AMU there, that is pretty much the same height, a 50-50 split, you are confident that you've got bromine in your molecule. So make sure you've got that in your notes. M and M+2 same height, presence of bromine. Okay. And the reason, and the other thing to look out for, right? Bromine's got two isotopes, bromine 79, bromine 81. Look at this, they get kicked off, right? But they give the same propyl cation. Okay, so electron bombardment is more likely to kick a lone pair off of electron because it's a loose, kick a lone pair of electrons off of bromine because they're more loosely held. But then once that happened, the weakest bond breaks, the carbon-bromine bond, okay? But it goes heterolytically. See that arrow type right there? Both the electrons go to bromine because it's more electronegative. So it gives us a giant peak for the propyl cation. Doesn't matter which bromine left, they weigh different amounts, but the propyl cation that's left over is the same. That's why we get that big peak there. So understand two isotopes of bromine, 50-50 split, that's an instant clue. Same thing for chlorine, okay? Chlorine, M and M+2 at about a 3-to-1 ratio. Okay? Instant clue that you have chlorine. That notable M+2 peak is a clue for chlorine and bromine. Okay? Now in this situation, the carbon-carbon bond and the carbon-chlorine bond are much closer in terms of the bond strength, okay? Whereas a carbon-bromine bond was weaker. Right? So the carbon-chlorine bond breaks heterolytically. Both of the electrons go to chlorine, but the carbon-carbon bonds break homolytically, right? Which is why we see peaks at 63 and 65 here. Another set of peaks where we see M and M+2 at a 3-to-1 ratio is more of a clue for the presence of chlorine. And this is what that looks like. Again, electron bombardment, we kick off a lone pair, or sorry, a single electron off of chlorine here, be it chlorine 35 or chlorine 37. Right? If we lose a chlorine, then it was a heterolytic cleavage just like we saw before. But if we have a carbon bond breaking, an alpha cleavage, right, cleavage of a bond group to the, or bond, cleavage of a group bonded to the alpha carbon, right, an alpha cleavage, right, in this case it's our methyl group that's being lost, right, that forms a stable cation because all of the atoms have a complete octet by kicking off that methyl group with a homolytic cleavage, right, that gets pumped out in mass spec, and we see two peaks there with complete octets, 63 and 65, maintaining that 3-to-1 ratio because of the two different chlorine isotopes. So these are just different things to look out for. When you look at a mass spec, right, on a test, you're expected to determine what's present. Those are some clues for chlorine and bromine. Okay. And then this is pretty much just explaining what I said before, right? Why do we do an alpha cleavage? That's what the mechanism looks like. Okay, because everything has a complete octet here. Okay. The alpha carbon, remember, is the one that's directly next to the functional group. And we only see that alpha cleavage with alkyl chlorides. We do not do it with alkyl bromides. Okay. And again, it's due to that difference in bond energy. See, carbon-chlorine, carbon-carbon, pretty similar. Carbon-bromine, much weaker bonds, so we just kick those bromines off. So that's alkyl halides. What about ethers? Okay. Fragmentation patterns of ethers are similar to alkyl halides, okay, except we don't maintain the same type of M and M+2 peaks. So what's happening? We have electron bombardment, kicks off a lone pair electron from oxygen in this case. Right? So then we form our radical cation here. And then we have two possibilities, right? If we're going to fragment. The first possibility is a heterolytic bond cleavage, where the electrons just go to oxygen because it's more electronegative, which is what we're seeing in this case. Either one of these bonds just breaking heterolytically. Okay? And then they're going to go to what's ever more electronegative, oxygen in this case. Okay? But the other possibility that we see here is that a carbon-carbon bond undergoes a homolytic bond cleavage at the alpha carbon to again form a more stable cation because everything has a complete octet, which we see in each one of these fragmentation types, losing different alpha carbons in each situation. Now, if we think about the peaks and which ones we're going to see be more prevalent, okay, 87, if we jump back and look, right, 87 is a little more prevalent than 101 because a primary radical that's formed as a byproduct is more stable than a methyl radical that's formed as a byproduct down here. Okay. So just more clues that can confirm what you have present looking at a mass spectrum. Okay. So ethers can undergo two possibilities: a heterolytic bond cleavage shown here, or a homolytic alpha cleavage shown here. Alcohols, next. Alcohols pretty much blow up. Okay, they really readily fragment, so they have very tiny molecular ion peaks. So another instant clue to put in your notes. The tiny molecular ion peak could be an alcohol. Not a guarantee, but it's a chance. Why do they fragment? Okay, well, we kick off a lone pair electron from oxygen in the electron bombardment, just like we did with an ether. Okay. Now, see, look at that tiny molecular ion peak. Remember, it'll be labeled for you. Okay. We kick off that lone pair electron, and then we pretty much immediately undergo an alpha cleavage. Okay. So now we've got that peak at 45 due to that really stable fragment that's formed. So alcohols also undergo an alpha cleavage, and you should know that alpha cleavage mechanism because this is the third time we've seen it. Right? It's a homolytic bond cleavage. But alcohols can also fragment in a different way, which is by the loss of water, which is shown here. Okay? And it's kind of weird to look at. Okay? In all the other cases in fragmentation, we only break one bond. But here, when we're losing water from an alcohol, we break two. And the reason for that, and the reason we break two bonds and move over to the gamma carbon over here, is because we could not have a radical right next to the carbocation. It'd be too unstable, right? So if our alcohol is off of the alpha carbon, we don't use it from the beta, we go one more to the gamma over here. Okay. And if there is a hydrogen on your gamma carbon, you're going to readily lose water because that's a stable fragment. So what you look out for, another thing to confirm the presence of an alcohol is, right, water weighs 18 atomic mass units. So if you see a big peak at whatever your molecular ion is, minus 18, that's a clue that you have an alcohol. Okay. Because alcohols fragment by losing water. So let's finish these fragmentation patterns with ketones. Okay. The last functional group we'll discuss common fragmentation patterns for. Okay. Again, electron bombardment. Step one, we lose a lone pair electron off of oxygen. Okay. Then an adjacent carbon-carbon bond breaks homolytically, right? Does an alpha cleavage, and we form a stable fragment due to these complete octets. Okay? Whichever forms the more stable radical is the more abundant peak. So here, primary radical is more stable than methyl radical, so our peak at 43 will be higher than our peak at 71. Weird to look at these triple bonded oxygens, okay, but they have complete octets, so they're present. If you have a gamma hydrogen, you look out for something that's known as a McLafferty rearrangement with ketones. Okay, so alpha, beta, gamma. If you have a hydrogen there, you will undergo a McLafferty rearrangement. And notice that with the case of a ketone, right, the carbonyl itself is considered the functional group. So if this was an alcohol, that would be the alpha carbon. But with a ketone, this whole thing is considered the functional group. So notice the alpha carbon's the next one over. Next, because the definition of an alpha carbon is next to the functional group. So this is an alpha carbon, this is an alpha carbon. So really you're going 1, 2, 3, 4 carbons away from a McLafferty rearrangement. Okay. And the reason for that is because you have a 6-membered transition state here to undergo the McLafferty rearrangement. And we know that those 6-membered rings are stable. Okay. We again break 2 bonds here. And the reason that we undergo a McLafferty rearrangement after the electron bombardment is because it produces a more stable alkene and completes the octet on oxygen, being more electronegative. Okay? So a McLafferty rearrangement. Be familiar with that mechanism. It's a series of homolytic bond cleavages, yep, which is shown here, and all that information that we've mentioned previously is summarized on this slide 39. Yep. So to wrap up, mass spec, just a couple other things to be on your radar, nothing that would be explicitly tested. Everything we've been discussing so far, right, has been that electron bombardment that was just mentioned, right? Electron ionization, that's all we're considering. Other things do exist to varying degrees. Okay? There's chemical ionization, right? So CI mass spec, where you spray it with a pre-ionized gas, and then you ionize your sample by electron or proton transfer. Okay? Chemical ionization, electron ionization require that the sample be vaporized, so they're only used for low molecular weight compounds. Okay? You got secondary ion mass spectrometry, photon mass spectrometry, right? MALDI, that's abbreviated. You might see that abbreviation. It's matrix-assisted laser desorption ionization, okay, hitting it with photons. Or you can even use neutral atoms, right? FAB is fast atom bombardment. With enough kinetic energy, you can ionize these things as well. Mass spec has to be connected to something to purify the sample, right? And typically, what you'll see that connected to is a gas chromatograph. Okay? Gas chromatography-Mass Spectrometry, or GCMS, is the total package. Okay? And what happens is you use a gas chromatograph, right? The lowest boiling point compound comes out first. Okay? Then it immediately goes from the GC into the mass spec. Okay? And then your mass spec reads your different sample. Okay, so you're separating something out and analyzing it all at once. Really common instrument. It's used in forensics, right? It's used in airports, all sorts of different applications, commonly found in labs as well. Okay, so just be aware that that exists. These fragmentation patterns and isotopes wrap up mass spec in 2 videos for us. Okay? For the rest of chapter 13, we will move on to IR and UV vis, but make sure before we get into that, you use video 1 and video 2 from chapter 13 to fully understand mass spec. Its biggest use is determining the formula using the rule of 13, and we will use some of those fragmentation patterns to make an educated guess of what is present in the molecule. Okay? We can confirm those things, as we'll see next, using IR.